At first, Alpha Centauri sounds close. It's the nearest star system to our own. So close, in fact, that you can spot it from the southern hemisphere with the naked eye, shining quietly, like it's been there forever. And it has a strange effect on the mind, because once you learn it's the closest, the next thought feels inevitable. So how long would it take us to get there? Not in science fiction, not through wormholes, not with magic engines, with real technology, real fuel, real limits. The unsettling truth is that closest in space doesn't mean what it means on Earth. In the universe, the nearest neighbor can still be an ocean so wide that a human lifetime becomes a rounding error. Our fastest spacecraft are already leaving the solar system, silent, fast, and unstoppable. But even at those speeds, Alpha Centauri doesn't get any closer. It stays where it is, a distant light separated from us by a gap of near-perfect emptiness, where time becomes the real cost of travel. And the moment you calculate that cost, the numbers stop feeling like numbers. They start feeling like eras. In this documentary, we're going to trace the journey in the only honest way, step by step, through what speed truly means in deep space, why the speed of light is such a brutal wall, and what would have to change for Alpha Centauri to become more than a star we stare at. Because the answer isn't just years. The answer is a choice between centuries and something far stranger. If you enjoy calm, late-night journeys into the deepest questions of space, subscribe to Theories Before Sleep, and let's begin. For most of human history, the stars were symbols. They marked seasons, they guided travelers, they inspired myths. They were never destinations. That changed the moment humanity learned what stars really are. Distant suns, scattered through space, governed by the same physics as our own. Suddenly, the night sky stopped being a ceiling and became a map. And among all those points of light, one system stands out: Alpha Centauri. Not because it is special in appearance, not because it hosts confirmed civilizations, but because it is close, closer than any other star system. And in space, closeness is deceptive. Alpha Centauri is not one star, but three: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Together, they form a gravitational family drifting through the Milky Way, locked in a slow cosmic dance. Proxima Centauri, the smallest and faintest, is the closest of the three. It lies just over 4 light-years away. 4 light-years. At first, that sounds manageable. After all, 4 is a small number. On Earth, 4 years is a short commitment. 4 kilometers is a walk. 4 hours is an afternoon. But in space, 4 hides something enormous. A light year is not a measure of time. It is a measure of distance. 1 light year is the distance light travels in a year, about 9.46 trillion kilometers. Multiply that by 4. The result is so large that writing it out feels abstract, almost meaningless. It is a number the human brain was never designed to intuitively understand. And yet, that number is the starting point for every honest discussion about traveling to Alpha Centauri. Because before asking how, we must confront how far. Even within our own solar system, distance dominates everything. Light takes about 8 minutes to travel from the Sun to Earth. It takes hours to reach the outer planets, days to reach the edge of the solar system. And beyond that edge lies interstellar space, an emptiness so vast that spacecraft can travel for years without encountering anything at all. The Voyager probes, launched in the 1970s, are the farthest human-made objects in existence. They are already drifting through interstellar space, farther from Earth than anything ever built. And yet, after decades of travel, they have not even begun the journey to Alpha Centauri. If Voyager were aimed directly at Alpha Centauri, it would take over 70,000 years to arrive. 70,000. That is not a typo. 70,000 years ago, modern humans were still painting animals on cave walls. Agriculture had not begun. Cities did not exist. Written language had not yet been invented. Civilizations rise and fall in spans far shorter than that. Even if Voyager's systems somehow survived, even if it never collided with a particle of dust, even if humanity itself vanished and re-emerged in different forms, Alpha Centauri would still be waiting. This is the first truth about interstellar travel. Speed is everything, and our current speeds are painfully slow. The fastest spacecraft ever launched by humanity, NASA's Parker Solar Probe, reaches speeds of around 430,000 miles per hour at its closest approach to the Sun. That sounds extraordinary. It is extraordinary. But even at that speed, a journey to Alpha Centauri would take roughly 6,600 years, still longer than all recorded human history. This is where the mind begins to resist. Surely there must be a faster way. Surely technology improves. And it does. But space does not care about progress in the way Earth does, because space imposes limits that technology cannot easily bend. The most famous of these limits is the speed of light. Nothing with mass can reach it. Nothing can exceed it. It is not just a speed. It is woven into the structure of reality itself. Light travels at about 300,000 kilometers per second. At that speed, Alpha Centauri is just over 4 years away. If we could travel at the speed of light, the journey would be measured in years, not millennia. But we cannot. Even reaching a significant fraction of light speed would require energy on a scale humanity has never produced for a single object. And energy is not the only problem. Acceleration matters. To reach high speeds, a spacecraft must accelerate and then decelerate at the destination. Otherwise, it would simply fly past Alpha Centauri at relativistic speed, unable to stop. That means carrying fuel not just to go fast, but to slow down, which means carrying more mass, which requires more energy, which requires more fuel. This is the tyranny of the rocket equation, a mathematical reality that punishes ambition. Every kilogram of fuel added requires more fuel to move it. The faster you want to go, the more brutally the equation works against you. Chemical rockets, the kind that took humans to the moon, are already near their practical limits. They are powerful but inefficient. Nuclear propulsion offers improvements, but not miracles. Even the most optimistic nuclear engines would still take centuries to reach Alpha Centauri. Then there is time itself. At extreme speeds, time behaves strangely. According to Einstein's relativity, clocks on fast-moving spacecraft run slower than clocks on Earth. This means that, in theory, a crew traveling near light speed could experience less time than observers back home. To the travelers, the journey might feel shorter, but to Earth, centuries could pass. This introduces a profound consequence. Interstellar travel is not just a journey through space. It is a journey through time. Anyone who leaves Earth for Alpha Centauri is effectively leaving their era behind. They would arrive in a future they never knew. Languages would change, cultures would transform, nations would rise and fall. There may be no one left who remembers why they were sent, and this is assuming the ship arrives intact. Interstellar space is not entirely empty. It is filled with sparse particles, radiation, and dust moving at incredible speeds, at relativistic velocities. Even a grain of dust becomes a bullet. A collision at near light speed would release enormous energy, enough to damage or destroy a spacecraft. Shielding against this would require mass. More mass means more fuel. The problem loops endlessly. Then there is radiation. Beyond the protective bubble of the sun's magnetic field, cosmic rays bombard space relentlessly. These high-energy particles can damage electronics and biological tissue over time. For a journey lasting decades, centuries, or longer, radiation becomes a silent threat, slow, cumulative, and deadly. Protecting humans from this environment is one of the hardest unsolved problems in space travel. We can shield machines, but humans are fragile. Bones weaken in microgravity. Muscles atrophy. Immune systems change. Psychological effects of isolation accumulate. A voyage to Alpha Centauri would not be a mission. It would be an entire civilization in transit. Generations would be born, live, and die aboard a ship that never sees a destination. And this leads to an uncomfortable realization. Traveling to Alpha Centauri with known physics does not resemble exploration as we imagine it. It resembles exile, a one-way departure into the unknown, with no guarantee of arrival and no return possible. And yet, despite all this, humanity keeps asking the question. Because Alpha Centauri represents something more than distance. It represents the boundary between what feels possible and what feels forbidden. It forces us to confront the scale of the universe honestly, without shortcuts. And as we begin to understand just how punishing that scale truly is, another question emerges naturally. If our fastest ships are far too slow, and light itself sets an unforgiving limit, what ideas have scientists proposed to bridge that gap? That is where the journey continues next. To understand how long it would take to reach Alpha Centauri, we have to confront a difficult truth. Distance alone is not the real enemy. The real enemy is energy. Because in space, movement is not limited by roads, terrain, or friction. It is limited by how much energy you can generate, store, and control, and how efficiently you can use it without destroying yourself in the process. This is why every serious proposal for interstellar travel eventually runs into the same wall. Not imagination, physics. The first approach humanity ever mastered was chemical propulsion. This is the technology that lifted rockets off Earth, carried astronauts to the moon, and sent probes to the outer planets. Chemical rockets work by expelling mass at high speed. They are powerful, reliable, and well understood. But they are also inefficient. Only a small fraction of the energy stored in chemical fuel becomes forward motion. Most of it is lost as heat. This is not a design flaw. It is a fundamental limit of chemistry. Even if we built the largest chemical rocket ever imagined, one far larger than anything launched today, it would still struggle to reach a tiny fraction of light speed. And a tiny fraction is not enough. At 1% of the speed of light, a journey to Alpha Centauri would take more than 400 years. That is 4 centuries in transit. 4 centuries of maintaining life support systems, structural integrity, and social stability. 4 centuries of isolation. This is why chemical propulsion is not considered viable for interstellar travel. So scientists turn to nuclear energy. Nuclear reactions release millions of times more energy than chemical reactions. In theory, this makes them ideal for deep space propulsion. The first major concept was nuclear thermal propulsion. In this design, a nuclear reactor heats a propellant, usually hydrogen, and expels it at high speed to produce thrust. This approach is far more efficient than chemical rockets. It could cut travel times within the solar system dramatically, but interstellar distances remain unforgiving. Even with nuclear thermal propulsion, reaching Alpha Centauri would still take hundreds or thousands of years. Nuclear electric propulsion, using reactors to power ion engines, offers even greater efficiency, but at the cost of extremely low thrust. These engines accelerate spacecraft slowly over long periods. They are excellent for robotic probes. They are not suitable for transporting humans across interstellar space. Then there is nuclear fusion. Fusion powers the stars themselves. If humanity could harness it efficiently, it could transform space travel. Fusion propulsion concepts imagine engines that fuse hydrogen isotopes to produce enormous energy, expelling reaction products as high-speed exhaust. In theory, fusion could propel spacecraft to significant fractions of light speed. In practice, controlled fusion has proven extraordinarily difficult. Despite decades of research, humanity has not yet built a fusion reactor that produces more energy than it consumes in a sustained, practical way. Even if that hurdle were overcome, building a fusion engine compact, stable, and reliable enough for a spacecraft would introduce a new set of challenges. Then comes the problem of fuel. Fusion requires rare isotopes like deuterium or helium-3. Mining, storing, and handling these materials at the scale needed for interstellar travel would be a monumental undertaking. Still, fusion remains one of the more realistic long-term possibilities for reducing travel times to centuries rather than millennia. But even centuries raise uncomfortable questions. Who is the mission really for? The people who launch it, or the people who arrive? This is where the concept of generation ships enters the discussion. A generation ship is not designed to transport a crew to Alpha Centauri within a single lifetime. Instead, it would function as a self-contained world, sustaining multiple generations of humans as the ship slowly crosses interstellar space. Children would be born aboard the ship. They would live their entire lives inside it. They would die without ever seeing Earth. Alpha Centauri would be a story passed down through generations, a destination promised but never personally known. This idea solves the problem of time in one sense, but creates new problems. A generation ship would need to be completely self-sufficient. Food, water, air, and energy would need to be recycled almost perfectly for centuries. Any failure, biological, mechanical, or social, could doom the entire mission. There is also the psychological challenge. Humans evolved to live under open skies, on a planet with natural cycles of day and night, seasons, and weather. Living inside a metal structure for generations Knowing that the outside environment is instantly lethal could produce profound psychological stress. Social cohesion would be essential. Conflict, rebellion, or cultural collapse could end the mission long before arrival. Then there is another issue rarely discussed. Why would the descendants of the original crew continue the mission? They did not choose to leave Earth. They did not agree to the journey. They might decide that maintaining the ship is not worth the effort, that turning inward is easier than pushing toward a distant star they have never seen. In that case, the mission would simply stop. The ship would become a drifting artifact, a sealed world without purpose. Another proposal attempts to avoid this problem by eliminating humans entirely. Robotic probes do not need air, food, or psychological comfort. They can endure radiation, cold, and isolation far better than humans. This makes them ideal candidates for interstellar exploration. But even robotic probes face energy limits. A probe traveling at 10% of the speed of light would still take over 40 years to reach Alpha Centauri. 40 years is manageable for machines, but not trivial. Electronics degrade. Systems fail. Unexpected events accumulate. Designing a probe that can operate autonomously for half a century, make scientific decisions, and transmit data back across light years is a formidable challenge. And transmission itself is a problem. Signals weaken with distance. By the time a probe reaches Alpha Centauri, its messages would take over 4 years to return to Earth. Any malfunction would already be history by the time Earth learns about it. This brings us to one of the most radical ideas ever proposed for interstellar travel: light sails. Instead of carrying massive amounts of fuel, a spacecraft could be pushed by light itself, either from the sun or from powerful lasers stationed near Earth. Photons carry momentum. When they strike a reflective surface, they transfer a tiny amount of force. With a large enough sail and a powerful enough light source, that force could accelerate a spacecraft to extreme speeds. Projects like Breakthrough Starshot have explored this idea seriously. The concept envisions gram-scale probes attached to ultra-thin sails, accelerated to about 20% of the speed of light by Earth-based lasers. At that speed, the journey to Alpha Centauri would take about 20 years. For the first time, interstellar travel begins to fit within a human lifetime. But the price is severe. These probes would be tiny. They could carry minimal instruments. They could not slow down upon arrival. They would pass through the Alpha Centauri system in hours or days, collecting whatever data they could in a brief, violent flyby. And even this depends on technologies that do not yet exist at the required scale. Lasers more powerful than any ever built, materials stronger and lighter than anything currently known, and precision targeting across light years. Still, light sails represent something important. They mark the first time humanity has proposed an interstellar journey measured in decades instead of centuries. But even here, a final obstacle remains: human travel. A gram-scale probe can survive acceleration forces that would crush a human body instantly. Scaling light sail technology up to human-sized spacecraft would reintroduce mass, energy, and shielding problems. The physics does not change, only the scale does. And scale is unforgiving. So by the end of every serious analysis, we arrive at the same conclusion. With known physics and realistic engineering, traveling to Alpha Centauri would take tens of thousands of years with current probes, thousands of years with advanced nuclear propulsion, hundreds of years with optimistic fusion concepts, decades only for tiny unmanned probes. Human travel remains far beyond reach, and this leads to the deeper question that lingers beneath all these calculations. If the universe allows us to see Alpha Centauri clearly, if it allows us to detect planets there, if it tempts us with proximity, why does it make reaching it so brutally difficult? The answer may lie not in engineering, but in the nature of space and time themselves. And that is where the journey continues next. To understand why Alpha Centauri remains so stubbornly out of reach, even after exploring propulsion concepts and futuristic technologies, we need to step back and look at something deeper than engines. We need to look at space-time itself, because interstellar travel is not just about moving through space. It is about how space and time are structured at the most fundamental level. Albert Einstein showed us that space and time are not separate things. They are woven together into a single fabric called space-time. Objects with mass and energy bend this fabric, and that curvature determines how matter and light move. This insight revolutionized physics, but it also revealed a hard limit. The speed of light is not arbitrary. It is a structural feature of the universe. Light speed is the maximum speed at which information, energy, or causality can travel. It is not just difficult to reach. It is woven into how reality works. As an object with mass accelerates, it does not simply go faster in a linear way. Its energy increases disproportionately. As it approaches the speed of light, the energy required to accelerate it further rises dramatically, approaching infinity. This means that reaching light speed would require infinite energy, not large energy, infinite energy, which makes it impossible. This is why faster-than-light travel, as imagined in science fiction, faces such severe problems. If information could travel faster than light, cause and effect could break down. Events could influence the past. Paradoxes would arise. The universe seems to forbid this, not by chance, but by design. So when we ask how long it would take to reach Alpha Centauri, we are really asking how close we can approach this cosmic speed limit without tearing ourselves apart. And the answer, so far, is not very close. Even reaching 10% of light speed is an extraordinary challenge. At that speed, time dilation becomes noticeable. For the travelers, time would pass slightly more slowly than for observers on Earth, but not enough to turn centuries into years. To reduce a 4-year light speed journey into something that feels like a few months on board would require speeds so close to light speed that the energy demands become absurd. But energy is not the only issue. Acceleration matters just as much. Humans can tolerate only limited acceleration over long periods. A spacecraft accelerating at 1 Earth gravity would be comfortable, but even at that gentle acceleration, reaching near light speed would take years of continuous thrust, years of burning fuel, years of producing waste heat, years of maintaining flawless engine performance, and then, at the destination, the ship would need to decelerate for the same length of time. The journey becomes symmetrical. Acceleration out, cruise, deceleration in. Every phase compounds the challenge. And then there is heat. Any propulsion system powerful enough to accelerate a spacecraft to relativistic speeds will generate enormous amounts of waste heat. In space, There is no air to carry heat away. The only way to lose heat is by radiating it. Radiators would need to be massive. Mass adds energy requirements. Again, the loop tightens. Then there is the problem of collision. At interstellar speeds, space is no longer forgiving. Even though interstellar space is extremely empty, it is not perfectly empty. Atoms of hydrogen drift between stars. Tiny grains of dust float through the darkness. At everyday speeds, these particles are harmless. At relativistic speeds, they become catastrophic. A single hydrogen atom impacting a spacecraft at a significant fraction of light speed releases energy comparable to high-energy radiation. A dust grain could punch through shielding like a weapon. To survive this environment, a spacecraft would need thick shielding, possibly meters thick. Shielding means mass. Mass means energy. The equation never loosens its grip. Even if shielding were solved, radiation would remain a constant threat. At high speeds, cosmic radiation becomes more intense due to relativistic effects. Particles appear more energetic in the spacecraft's frame of reference. This radiation would damage electronics and living tissue relentlessly. Long-term exposure would be lethal without extraordinary protection. So when we imagine a ship crossing interstellar space at high speed, we are not imagining a sleek vessel gliding smoothly through emptiness. We are imagining an object being hammered continuously by invisible forces, radiation, particles, and energy flows that scale with speed. The faster you go, the harsher the universe becomes. This suggests something unsettling. The universe may be navigable, but not easily crossed. Local exploration within solar systems appears possible, though difficult. But interstellar travel confronts us with conditions that grow hostile, not gradually, but exponentially. And this may not be an accident. Some physicists have suggested that the universe is structured in such a way that advanced civilizations are encouraged to look outward, but not to spread rapidly. Observation is cheap. Travel is expensive. Telescopes allow us to learn about distant stars and planets without leaving home. Spectroscopy lets us analyze atmospheres light years away. Signals travel easily. Matter does not. This asymmetry favors knowledge over expansion, understanding over conquest. Then there is another effect of relativity that complicates matters further. Simultaneity. At high speeds, different observers disagree about what events are happening at the same time. For a spacecraft traveling near light speed, the timeline of Earth would appear distorted. Communication becomes not just delayed, but conceptually fragmented. Coordinating missions, receiving instructions, or responding to emergencies becomes almost meaningless when messages take years to arrive and frames of reference disagree about time itself. This turns interstellar travel into something more than a logistical challenge. It becomes a philosophical one. What does it mean to belong to a civilization when you are cut off, not just by distance, but by time? Then there is gravity. Escaping Earth is only the beginning. A spacecraft must climb out of the sun's gravity well, then survive the weak but persistent gravitational influences of stars, gas clouds, and the galaxy itself. Navigation over light years requires extraordinary precision. Small errors compound over time. A tiny deviation early in the journey could mean missing the target star by millions of kilometers decades later. Corrections require fuel. Fuel requires mass. Again, the loop closes. All of this leads to a realization that is difficult to accept. Interstellar travel is not hard in the same way that flying was hard before airplanes. It is hard in a deeper way. It pushes against the architecture of reality itself. This does not mean interstellar travel is absolutely impossible, but it may be deliberately impractical. So impractical that only civilizations with immense resources, patience, and stability could even attempt it, and even then only under extreme constraints, which raises an uncomfortable possibility. Maybe Alpha Centauri is not meant to be reached by travelers. Maybe it is meant to be reached by thinkers, by observers, by civilizations that learn to understand the universe without crossing every gap physically. And yet, humanity keeps imagining the journey, because the pull of the stars is not rational. It is emotional. Alpha Centauri is close enough to feel reachable, yet far enough to resist every shortcut. It sits exactly at the edge of our technological dreams. And that is why it matters, because at that edge, we are forced to confront the difference between what we want to do and what the universe allows. And as we begin to grasp that difference, another question emerges. If space-time itself resists interstellar travel, are there any loopholes hiding in the equations? Or is the barrier absolute? That is where the journey continues next. If space-time itself resists interstellar travel, then the natural response is to ask whether physics hides any exceptions, any cracks in the wall that might allow passage without crossing the full distance in the usual way. For decades, scientists have searched for such loopholes, not out of fantasy, but out of mathematics. Because sometimes the equations allow possibilities that intuition does not. One of the most famous ideas to emerge from this search is the concept of the wormhole. In theory, a wormhole is a shortcut through space-time, a tunnel connecting two distant regions. Instead of traveling across space, you travel through it, entering at one point and exiting somewhere else entirely. If such a structure existed and were stable, the journey to Alpha Centauri could take minutes instead of millennia. But there is a problem. Wormholes are mathematical solutions, not known physical objects. They arise naturally in Einstein's equations, but only under conditions that appear incompatible with reality as we understand it. To remain open, a wormhole would require exotic matter, a form of matter with negative energy density. This is not simply rare matter. It is matter that behaves in ways we have never observed at macroscopic scales. Small quantum effects can produce negative energy densities for extremely brief moments. But scaling this up to something large enough for a spacecraft remains far beyond known physics. Without exotic matter, a wormhole would collapse instantly, pinching itself off before anything could pass through. Even if a stable wormhole could exist, it would introduce profound dangers. The slightest disturbance could destabilize it. Radiation passing through might cause it to collapse. Gravitational forces could tear it apart. And then there is the issue of time. Many wormhole solutions allow not only travel through space, but travel through time. This leads to paradoxes that challenge causality itself. The universe appears hostile to such arrangements, which suggests that if wormholes are possible at all, they may be forbidden from being used. Another proposed loophole is the warp drive. Popularized by science fiction, the warp drive does not move a spacecraft through space faster than light. Instead, it moves space itself. The idea is deceptively simple. Space in front of the ship contracts. Space behind the ship expands. The ship sits in a bubble of space-time, effectively riding a wave. Locally, it never exceeds the speed of light. Globally, it appears to travel faster than light. In 1994, physicist Miguel Alcubierre showed that such a space-time configuration is mathematically possible within general relativity. For a moment, it seemed like a breakthrough, but again, reality intervened. The Alcubierre drive requires enormous amounts of negative energy, far more than the total energy output of stars. Early calculations suggested it would require more energy than exists in the observable universe. Later refinements reduced the energy requirement, but not enough to make the concept realistic. And even if the energy problem was solved, new issues appear. Warp bubbles may trap lethal radiation. Creating or collapsing the bubble could release catastrophic energy. Steering and stopping would be extraordinarily dangerous. There is also the question of causality. Like wormholes, warp drives may allow violations of cause and effect. Signals could arrive before they were sent. Time itself becomes unstable. Once again, the universe seems to tolerate the mathematics, but resist the implementation. Another idea involves manipulating space-time using cosmic strings, hypothetical one-dimensional defects left over from the early universe. If two such strings existed and were arranged correctly, they might allow effective faster-than-light travel. But cosmic strings, if they exist at all, are extraordinarily rare and incredibly massive. No evidence of usable cosmic strings has ever been found. Then there is quantum teleportation. Despite the name, it does not move matter through space. It transfers information about quantum states. The original object is destroyed, and the state is recreated elsewhere. This process does not violate the speed of light. It still requires classical communication, which travels no faster than light. Teleporting a human, or even a complex object, would require measuring and transmitting astronomical amounts of information with perfect accuracy. It is not just impractical, it may be fundamentally impossible. Then there is the idea of suspended animation or cryogenic sleep. Instead of shortening the journey, you lengthen the traveler's endurance. If humans could be placed in deep hibernation, aging slowed or paused, a centuries-long voyage might become psychologically tolerable. But biology does not cooperate easily. Freezing cells damages them. Long-term inactivity causes tissue degradation. Reviving complex organisms without injury remains unsolved. Even if cryogenic sleep became possible, it would not solve the societal problem. A ship arriving centuries later would still encounter a future that may not recognize it. And there is a deeper problem that undercuts all these ideas. Even if a loophole existed, even if a civilization could exploit it, the universe would still impose costs. Energy must come from somewhere. Entropy must increase. Stability must be maintained. Shortcuts do not remove responsibility. They only concentrate risk. This leads to an unsettling thought. Perhaps interstellar travel is not forbidden, but perhaps it is intentionally made rare. Rare enough that civilizations must choose carefully whether to attempt it. Rare enough that reckless expansion is discouraged. In this view, the universe allows intelligence to arise, to observe, to understand, but not to spread uncontrollably. The stars are visible, but distant, reachable in theory, but punishing in practice. This does not make the universe cruel. It makes it selective, and selection shapes behavior. A civilization that survives long enough to attempt interstellar travel must be patient, stable, cooperative, and extraordinarily careful. It must value knowledge over conquest, understanding over speed, and perhaps that is the final filter. Not whether a civilization can build a fast enough ship, but whether it can endure long enough, wisely enough, to justify the journey. Alpha Centauri may not be unreachable because of a lack of imagination. It may be unreachable because imagination alone is not enough. And as we begin to see how every apparent loophole closes under scrutiny, one final realization emerges. The challenge of reaching Alpha Centauri is not only technical, it is existential. It forces us to ask what kind of civilization we are and what kind we are willing to become. And that brings us to the next question. If shortcuts through space-time remain out of reach, what would it actually mean, culturally and morally, to attempt the journey anyway? That is where the story continues next. If reaching Alpha Centauri requires centuries, generations, or technologies that push the edge of reality itself, then the question shifts again. Not can we go, but should we? Because the moment interstellar travel becomes even theoretically possible, it stops being a purely scientific problem and becomes a cultural, ethical, and moral one. Sending humans to another star is not like launching a probe. It is a decision that affects lives not yet born, a commitment that binds future generations to choices they did not make. This is where the idea of the interstellar mission changes character. It is no longer an expedition. It becomes a social experiment on a cosmic scale. Consider the generation ship again, but not as a technical object. Consider it as a society, a closed world isolated from Earth, drifting through interstellar darkness for centuries. Every aspect of life inside that ship would be shaped by the journey. Education would not prepare children for Earth, but for maintenance, survival, and continuity. Culture would evolve under artificial skies. Myths, stories, and beliefs would grow around a destination no one has ever seen. Alpha Centauri would not be a place. It would be an idea. And ideas change. Over time, belief in the mission could weaken. New values could emerge. Future generations might ask a question their ancestors never allowed themselves to ask. Why are we still going? At what point does a mission become an obligation rather than a purpose? This is not a hypothetical concern. Even on Earth, long-term projects struggle to survive political change, economic collapse, and cultural shifts. A mission lasting centuries would need an unprecedented level of stability, not just technological, but ideological. The ship would need rules, governance, conflict resolution, justice, all without external authority. Every mistake would be permanent. There would be no rescue, no reinforcement, no fresh start. And then there is the question of consent. The first generation might volunteer, but their children would be born into confinement with no possibility of leaving. Is it ethical to create life inside a vessel that has no escape, no open sky, and no choice of destination? Some argue that this is no different from being born on Earth. You do not choose your planet. But Earth offers freedom of movement, diversity of environments, and a living biosphere. A ship offers none of these. Its limits are absolute. Every wall is final. This raises a deeper question about human dignity. Is survival alone enough? Or does being human require openness, unpredictability, and contact with the living world. Then there is the issue of arrival. Suppose the ship reaches Alpha Centauri. What if the system is hostile? What if its planets are uninhabitable? What if conditions are worse than expected? The mission cannot turn back. Everything depends on assumptions made centuries earlier. Science improves, but it does not guarantee comfort. A single miscalculation could turn a generational sacrifice into a dead end. This risk would weigh heavily on any civilization mature enough to consider the journey. Another ethical dimension emerges when we consider what or who might already exist at the destination. Even if Alpha Centauri harbors only microbial life, does humanity have the right to alter that environment? Introducing Earth life could wipe out native ecosystems before they are even understood. And if intelligent life exists, however unlikely, the implications are even more serious. Interstellar travel is not neutral. It is an intervention. It changes places forever, which brings us to a crucial realization. For most of history, exploration was justified by expansion, survival, or conquest. Those motivations shaped how humans treated new lands and new peoples. But space does not offer the same moral cover. There are no empty continents, no unclaimed worlds. Every planet has a history written in chemistry, geology, and time. Reaching another star would force humanity to confront its legacy as an explorer species and decide whether it has learned from its past. Then there is the question of priority. Resources spent on interstellar missions are resources not spent on Earth. Addressing climate change, inequality, disease, and conflict may matter more than chasing distant stars. Some argue that interstellar travel is a distraction. Others argue that it is an insurance policy, a way to ensure that humanity does not vanish with its home planet. Both views carry weight, but they lead to different futures. A civilization that chooses interstellar travel must first become capable of long-term thinking, global cooperation, and restraint. It must solve its internal problems before exporting itself into the universe. Otherwise, it risks carrying its worst traits with it. There is also a psychological cost to consider. Knowing that a mission will outlast your life can be empowering or devastating. For some, contributing to a project that benefits distant descendants. For most of human history, the stars were symbols. They marked seasons. They guided travelers. They inspired myths. They were never destinations. That changed the moment humanity learned what stars really are. Distant suns, scattered through space, governed by the same physics as our own. Suddenly, the night sky stopped being a ceiling and became a map. And among all those points of light, one system stands out. Alpha Centauri. Not because it is special in appearance, not because it hosts confirmed civilizations, but because it is close, closer than any other star system. And in space, closeness is deceptive. Alpha Centauri is not one star, but three. Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Together, they form a gravitational family drifting through the Milky Way, locked in a slow cosmic dance. Proxima Centauri, the smallest and faintest, is the closest of the three. It lies just over 4 light-years away. 4 light-years. At first, that sounds manageable. After all, 4 is a small number. On Earth, 4 years is a short commitment. 4 kilometers is a walk. 4 hours is an afternoon. But in space, 4 hides something enormous. A light-year is not a measure of time. It is a measure of distance. 1 light year is the distance light travels in a year, about 9.46 trillion kilometers. Multiply that by 4. The result is so large that writing it out feels abstract, almost meaningless. It is a number the human brain was never designed to intuitively understand. And yet, that number is the starting point for every honest discussion about traveling to Alpha Centauri. Because before asking how, we must confront how far. Even within our own solar system, distance dominates everything. Light takes about 8 minutes to travel from the Sun to Earth. It takes hours to reach the outer planets, days to reach the edge of the solar system. And beyond that edge lies interstellar space, an emptiness so vast that spacecraft can travel for years without encountering anything at all. The Voyager probes, launched in the 1970s, are the farthest human-made objects in existence. They are already drifting through interstellar space, farther from Earth than anything ever built. And yet, after decades of travel, they have not even begun the journey to Alpha Centauri. If Voyager were aimed directly at Alpha Centauri, it would take over 70,000 years to arrive. 70,000. That is not a typo. 70,000 years ago, modern humans were still painting animals on cave walls. Agriculture had not begun. Cities did not exist. Written language had not yet been invented. Civilizations rise and fall in spans far shorter than that. Even if Voyager's systems somehow survived, even if it never collided with a particle of dust, even if humanity itself vanished and re-emerged in different forms, Alpha Centauri would still be waiting. This is the first truth about interstellar travel. Speed is everything, and our current speeds are painfully slow. The fastest spacecraft ever launched by humanity, NASA's Parker solar probe, reaches speeds of around 430,000 miles per hour at its closest approach to the Sun. That sounds extraordinary. It is extraordinary. But even at that speed, a journey to Alpha Centauri would take roughly 6,600 years, still longer than all recorded human history. This is where the mind begins to resist. Surely there must be a faster way. Surely technology improves. And it does. But space does not care about progress in the way Earth does, because space imposes limits that technology cannot easily bend. The most famous of these limits is the speed of light. Nothing with mass can reach it. Nothing can exceed it. It is not just a speed. It is woven into the structure of reality itself. Light travels at about 300,000 kilometers per second. At that speed, Alpha Centauri is just over 4 years away. If we could travel at the speed of light, the journey would be measured in years, not millennia. But we cannot. Even reaching a significant fraction of light speed would require energy on a scale humanity has never produced for a single object. And energy is not the only problem. Acceleration matters. To reach high speeds, a spacecraft must accelerate and then decelerate at the destination. Otherwise, it would simply fly past Alpha Centauri at relativistic speed, unable to stop. That means carrying fuel not just to go fast, but to slow down, which means carrying more mass, which requires more energy, which requires more fuel. This is the tyranny of the rocket equation, a mathematical reality that punishes ambition. Every kilogram of fuel added requires more fuel to move it. The faster you want to go, the more brutally the equation works against you. Chemical rockets, the kind that took humans to the moon, are already near their practical limits. They are powerful but inefficient. Nuclear propulsion offers improvements, but not miracles. Even the most optimistic nuclear engines would still take centuries to reach Alpha Centauri. Then there is time itself. At extreme speeds, time behaves strangely. According to Einstein's relativity, clocks on fast-moving spacecraft run slower than clocks on Earth. This means that, in theory, a crew traveling near light speed could experience less time than observers back home. To the travelers, the journey might feel shorter, but to Earth, centuries could pass. This introduces a profound consequence. Interstellar travel is not just a journey through space. It is a journey through time. Anyone who leaves Earth for Alpha Centauri is effectively leaving their era behind. They would arrive in a future they never knew. Languages would change, cultures would transform, nations would rise and fall. There may be no one left who remembers why they were sent, and this is assuming the ship arrives intact. Interstellar space is not entirely empty. It is filled with sparse particles, radiation, and dust moving at incredible speeds. At relativistic velocities, even a grain of dust becomes a bullet. A collision at near light speed would release enormous energy, enough to damage or destroy a spacecraft. Shielding against this would require mass. More mass means more fuel. The problem loops endlessly. Then there is radiation. Beyond the protective bubble of the sun's magnetic field, cosmic rays bombard space relentlessly. These high-energy particles can damage electronics and biological tissue over time. For a journey lasting decades, centuries, or longer, radiation becomes a silent threat, slow, cumulative, and deadly. Protecting humans from this environment is one of the hardest unsolved problems in space travel. We can shield machines, but humans are fragile. Bones weaken in microgravity. Muscles atrophy. Immune systems change. Psychological effects of isolation accumulate. A voyage to Alpha Centauri would not be a mission. It would be an entire civilization in transit. Generations would be born, live, and die aboard a ship that never sees a destination. And this leads to an uncomfortable realization. Traveling to Alpha Centauri with known physics does not resemble exploration as we imagine it. It resembles exile, a one-way departure into the unknown, with no guarantee of arrival and no return possible. And yet, despite all this, humanity keeps asking the question. Because Alpha Centauri represents something more than distance. It represents the boundary between what feels possible and what feels forbidden. It forces us to confront the scale of the universe honestly, without shortcuts. And as we begin to understand just how punishing that scale truly is, another question emerges naturally. If our fastest ships are far too slow, and light itself sets an unforgiving limit, what ideas have scientists proposed to bridge that gap? That is where the journey continues next. To understand how long it would take to reach Alpha Centauri, we have to confront a difficult truth. Distance alone is not the real enemy. The real enemy is energy. Because in space, movement is not limited by roads, terrain, or friction. It is limited by how much energy you can generate, store, and control, and how efficiently you can use it without destroying yourself in the process. This is why every serious proposal for interstellar travel eventually runs into the same wall. Not imagination, physics, The first approach humanity ever mastered was chemical propulsion. This is the technology that lifted rockets off Earth, carried astronauts to the moon, and sent probes to the outer planets. If interstellar travel reshapes human identity, then its final consequence is even broader. It reshapes humanity's place in the universe, not physically at first, but conceptually, because for most of our existence, humanity has lived inside a small bubble of meaning. Earth felt central, the sun felt special, the night sky felt distant and unreachable. Modern astronomy shattered that illusion. We now know that Earth is one planet among billions, orbiting one star among hundreds of billions in a single galaxy. One galaxy among trillions. Yet despite this knowledge, our daily lives remain grounded on a single world. Emotionally, Earth still feels like the center. Interstellar travel would change that. The moment humanity commits to a journey to Alpha Centauri, it symbolically accepts that Earth is not the final stage of its story. Earth becomes a beginning, a birthplace, not a boundary. This shift may be one of the most profound transformations any civilization can undergo, because once Earth is no longer the sole frame of reference, questions of meaning expand. History stops being planetary. Future stops being local. Responsibility stops being short-term. Humanity would begin to think in stellar terms. This doesn't mean abandoning Earth. It means recontextualizing it. Earth would become something precious, not because it is unique, but because it is fragile, a rare oasis of life in a universe that is mostly hostile. Ironically, the farther humanity looks outward, the more valuable Earth becomes. This is already happening. Astronauts who see Earth from space often describe a powerful emotional shift. Borders disappear. Conflicts seem small. The atmosphere looks thin and vulnerable. Interstellar thinking would amplify this perspective. If Earth is one world among many, then destroying it becomes not just a tragedy, but an irrational act. There is no backup Earth. Not easily. Not for a very long time. An Alpha Centauri will not save us from ourselves. It may offer knowledge, possibility, perspective, but it cannot replace responsibility. Another consequence of interstellar awareness is humility. The universe does not revolve around us. Stars form and die without regard for life. Galaxies collide over billions of years. Cosmic events unfold on scales so vast that human existence barely registers. This realization can feel unsettling, but it can also be grounding. It reminds humanity that meaning is not handed down by the universe. It is created. If we travel to Alpha Centauri and find nothing, no life, no habitable worlds, that emptiness will speak loudly. It will say that life is rare, and rarity creates value. If we find life, simple or complex, the implications are even greater. Humanity would no longer be alone, not philosophically, not biologically. Even the discovery of microbial life would mean that life emerges naturally when conditions allow, that the universe may be quietly alive. In either case, humanity's self-image changes. We stop being the sole example, or we stop taking that role for granted. Then there is the question of legacy. Civilizations often measure success by expansion, wealth, or power. Interstellar travel introduces a different metric: longevity. A civilization capable of launching a mission to Alpha Centauri must survive long enough to plan it, fund it, execute it, and sustain it. This requires stability on timescales humanity has never achieved. Wars, collapses, and internal divisions become existential threats, not just locally, but globally. Interstellar ambition encourages long-term cooperation, not because it is morally superior, but because it is necessary. This may be one of the most important indirect effects of aiming for the stars. The goal itself forces maturity. Then there is the cultural shift. Stories would change, art would change, philosophy would change. When humanity knows it can leave its home star system, even if only in theory, the universe stops feeling abstract. It becomes reachable, not now, not easily, but someday. This changes how future generations imagine themselves. Children growing up under that awareness would not ask only, "What will I do with my life?" They might ask, "Where does humanity go next?" That is a very different question. Another consequence is restraint. Knowing how difficult interstellar travel truly is discourages reckless expansion. It teaches that spreading across the stars is not inevitable. It must be earned. And earning it requires wisdom, patience, and care. This may explain something subtle about the universe. The stars are visible. Their planets are detectable. Their signals can reach us. But reaching them physically is hard, very hard, as if the universe allows awareness before access, understanding before possession. This pattern suggests that intelligence is meant to observe first, act later, to learn before touching. And perhaps that is the final role of Alpha Centauri in our story. Not as a destination to be conquered, but as a reminder of scale, a reminder of limits, a reminder of responsibility. Alpha Centauri sits just close enough to tempt us, just far enough to slow us down. And in that space between desire and difficulty, humanity is forced to grow, to think beyond generations, to question its motives, to decide what kind of civilization it wants to become. And so, when we ask how long it would take us to go to Alpha Centauri, the most honest answer may not be measured in years. It may be measured in maturity, in cooperation, in wisdom. Because before humanity can cross the distance between stars, it must first cross the distance between what it is and what it needs to be. And that brings us to the final reflection. If Alpha Centauri is not the next step in humanity's journey, then what is? That is where the story concludes. If Alpha Centauri is not the next physical step in humanity's journey, then the question becomes quieter, but deeper. What is the next step that actually matters? Because history shows that civilizations do not advance simply by moving farther outward. They advance by learning how to survive longer, understand more, and make better choices with the power they already have. And in that sense, the road to Alpha Centauri may begin much closer to home. Before humanity becomes an interstellar species, it must first become a stable one. This is not a poetic statement. It is a practical requirement. Any project that spans centuries demands continuity. Values must survive changes in leadership, culture, and circumstance. So far, no human civilization has demonstrated that kind of long-term stability. Empires rise and fall in centuries, or less. Political systems shift. Technologies are lost and rediscovered. Even written knowledge can vanish when societies collapse. Interstellar travel does not tolerate that fragility. A mission to Alpha Centauri would outlast nations, ideologies, and possibly even languages. It would require humanity to think not in election cycles or generations, but in millennia. That alone may be the greatest challenge of all. This shifts the focus of exploration inward, toward sustainability, toward resilience, toward the ability to maintain complex systems without collapse. In this view, learning to live responsibly on Earth is not separate from space exploration. It is a prerequisite. A civilization that cannot manage one planet is unlikely to succeed among the stars. Then there is the role of knowledge. The next step in humanity's journey may not be travel, but understanding. Telescopes already allow us to study Alpha Centauri's planets in ways unimaginable a few decades ago. Spectroscopy can analyze atmospheres light years away. Future observatories may detect weather patterns, surface features, or even signs of biological activity, all without sending a single spacecraft. This is a remarkable asymmetry. Information moves easily through the universe. Matter does not. Light travels freely. Knowledge accumulates cheaply. Travel remains expensive and dangerous. This suggests that the universe rewards curiosity more than expansion, and that observation may be enough, at least for now. Then there is the possibility that humanity's future is not defined by where it goes, but by how it exists. Advanced technologies may allow humans to live longer, healthier lives. Artificial intelligence may amplify understanding. Virtual environments may create experiences richer than physical travel for many purposes. This does not replace reality, but it changes the balance between physical presence and cognitive exploration. If you can model Alpha Centauri's planets in extraordinary detail, simulate their climates, and study their chemistry accurately, the urgency to physically visit them diminishes. The desire remains, but the necessity fades. This raises an uncomfortable possibility. Perhaps physical interstellar travel is not essential for a civilization to thrive. Perhaps awareness is enough. Another path forward is indirect exploration. Instead of sending humans, humanity may send generations of increasingly advanced probes. Each one builds on the knowledge of the last. Each one extends our reach a little farther. These probes become extensions of human perception. Eyes without bodies, curiosity without vulnerability. In this way, humanity can explore the galaxy without exposing itself to the most extreme risks. This may be the most realistic form of interstellar presence, not colonization, but observation. Then there is a more philosophical shift. Humanity has often defined progress as expansion, more land, more resources, more control. But the universe does not seem designed for that kind of progress. Resources are scattered, distances are vast, energy is costly. This encourages a different definition of advancement, one based on efficiency, understanding, and restraint. A civilization that learns to extract meaning rather than matter from the universe may endure longer than one that tries to dominate it. In this sense, Alpha Centauri becomes a symbol not of conquest, but of patience. It teaches that some goals are not meant to be rushed. Another important step in humanity's journey is learning how to share a future. Interstellar ambition requires cooperation on a global scale. No single nation can undertake such projects alone. No single ideology can sustain them. This forces humanity to confront its divisions. Either we learn to work together, or we remain confined to our home system. Space does not care about borders. Physics does not respect politics. The universe is indifferent to human disagreements. So the next step may not be outward, but collective, learning to think as a species. This is not a small step. It requires reimagining identity, responsibility, and success. Then there is the question of time again. Perhaps the most important realization Alpha Centauri offers is that urgency is a choice. The stars are not going anywhere. Alpha Centauri will still be there in 10,000 years. The universe does not demand haste. It allows time. Civilizations that rush may burn out. Civilizations that endure may eventually find paths that impatience cannot. This perspective reframes the question entirely. Instead of asking, how long would it take us to go to Alpha Centauri? We might ask, how long would it take us to become capable of doing so responsibly? And that answer may be longer than any travel time. But that does not make it meaningless. It makes it honest. Because the journey to Alpha Centauri is not just a technological milestone. It is a measure of who humanity has become. And perhaps the most profound realization is this. The universe does not reward speed. It rewards survival. It rewards understanding. It rewards civilizations that can live long enough to ask deep questions and patient enough to accept difficult answers. Alpha Centauri may remain out of reach for now, but in forcing us to confront distance, time, and limits, it already plays a role in humanity's story. It teaches us that not every journey begins with engines. Some begin with maturity. And as we reach this point in the story, one final thought remains. If the stars are not calling us to rush toward them, what are they calling us to become? That is the quiet question Alpha Centauri leaves behind. If the stars are calling humanity to become something more patient, more stable, and more thoughtful, then Alpha Centauri is not just a destination. It is a test of time, not the time measured by clocks or calendars, but the time measured by endurance. Because one of the hardest ideas for the human mind to accept is that some goals outlast us. Modern life trains us to expect results quickly. Progress is measured in months, success in years, relevance in moments. Even the longest projects most people encounter are designed to fit within a single lifetime. Interstellar travel breaks that pattern completely. A journey to Alpha Centauri forces humanity to think in terms of centuries or longer. It asks whether meaning can exist without personal completion, whether effort is worthwhile if the outcome belongs to distant descendants rather than ourselves. This idea is deeply uncomfortable, and yet it is not entirely new. Humanity has always relied on long chains of effort. Cathedrals took centuries to build. Agricultural systems were shaped over generations. Languages, laws, and knowledge were refined slowly, often without any single person seeing the finished result. Interstellar ambition simply extends this logic beyond anything we have attempted before. It asks, can a civilization value continuity more than immediacy? The challenge is not technological, it is psychological. Because long-term projects require trust that future generations will care about the same goals, maintain the same systems, and respect the sacrifices made before them. This trust is fragile. History shows that values shift, priorities change, and societies forget why certain paths were chosen. A generation ship drifting toward Alpha Centauri would depend on an unbroken chain of meaning. If that chain breaks, the mission ends, not with an explosion, but with indifference. This brings us to the concept of legacy. Most individuals think of legacy in small terms: family, reputation, personal impact. Interstellar travel forces a much broader perspective. The legacy of an interstellar mission would not be a monument or a name in a history book. It would be survival. The survival of knowledge, purpose, and cooperation across time, spans longer than recorded history. That kind of legacy cannot be enforced. It must be cultivated. Education would become central, not as a means to career advancement, but as a means of preservation. Every generation would need to understand not only how systems work, but why they exist. Rules would need context. Traditions would need explanation. Maintenance would become culture. Without this, complexity decays. Systems fail not because they are flawed, but because they are misunderstood. This is already visible on Earth. Technologies become opaque. Infrastructure ages. Knowledge becomes specialized and siloed. Interstellar travel magnifies this risk. A civilization attempting it would need to fight entropy, not just physically, but socially. Another layer of difficulty emerges when we consider motivation. Why would future generations continue a mission they did not choose? The answer cannot rely on authority alone. Force is unstable over long periods. Coercion breeds resistance. The mission would need to provide meaning, not just survival, but identity. People would need to see themselves as part of a story larger than any individual life. This is difficult in a world without open horizons. On Earth, meaning is reinforced by change, novelty, and interaction with nature. On a spacecraft, sameness dominates. The environment does not evolve naturally. Every change is deliberate. This could lead to stagnation, or it could lead to introspection. Much would depend on how culture evolves under these conditions. Then there is the issue of memory loss, not biological, but cultural. Over centuries, stories change. Details fade, symbols replace explanations, myths form. This is not inherently bad. Myths can preserve meaning even when details are lost. But myths can also distort reality. If the purpose of the journey becomes symbolic rather than practical, the mission risks drifting away from its original intent. Alpha Centauri could become a sacred idea rather than a destination. At that point, arrival may no longer matter. And that may not be failure. It may simply be transformation. Because perhaps the value of aiming for Alpha Centauri lies not in arrival, but in what the attempt creates along the way. A society that can sustain a long-term mission without collapse would possess qualities rare in human history: patience, cooperation, and humility. These qualities would be valuable regardless of the mission's outcome. This leads to another realization. Interstellar travel may be less about escaping Earth's limitations and more about confronting them honestly. It exposes weaknesses in governance, education, and social cohesion. It demands solutions to problems humanity often postpones. In this sense, Alpha Centauri functions like a mirror. It reflects what humanity is capable of sustaining, not for years, but for centuries. Then there is the quiet truth that even failure would be meaningful. A mission that turns back, stalls, or transforms into something else would still teach lessons about endurance, adaptability, and limits. Not every journey needs to succeed to be valuable. Sometimes the attempt itself reshapes the future. And yet, despite all these challenges, the idea persists, because humans are not satisfied with understanding alone. We want connection. We want presence. We want to know not just that Alpha Centauri exists, but what it feels like to be there. That desire is ancient. It drove migration across continents, voyages across oceans, and exploration of space itself. It is not rational. It is human. The question is not whether that desire will disappear, It is whether humanity can learn to hold it responsibly, to balance longing with restraint, ambition with patience, curiosity with care. As we approach the final reflection on this journey, one last dimension remains. If time, endurance, and legacy define the challenge of reaching Alpha Centauri, what happens if humanity simply waits? If it chooses not to rush, but to endure? What kind of future does patience create? That is where the story moves next, and where the journey begins to close. If humanity chooses patience over urgency, if it decides not to rush toward Alpha Centauri, but to endure, then the future unfolds along a very different path, a quieter path, one where progress is measured not by distance traveled, but by time survived, because waiting is not the same as doing nothing. Waiting can be an active choice. Civilizations that endure long enough may eventually find that the universe changes around them. Stars move, technologies evolve, understanding deepens. What is impossible in one era may become trivial in another, not through force, but through accumulation of insight. Alpha Centauri will not move closer in any meaningful way. The distance will remain. The laws of physics will remain. But humanity's relationship with those laws may change. History shows that the greatest transformations rarely come from speed alone. They come from refinement, the ability to store energy more efficiently, the ability to manipulate matter more precisely, the ability to model reality more accurately. None of these breakthroughs arrive suddenly. They emerge slowly, built on layers of previous understanding. A patient civilization invests in fundamentals, in mathematics, in physics, in materials science. These are not glamorous pursuits. They do not produce immediate spectacle, but they reshape what is possible, decades or centuries later. Flight did not begin with airplanes. It began with understanding air. Electricity did not begin with power grids. It began with curiosity about static charges. In the same way, interstellar travel, if it ever becomes feasible for humans, will not begin with engines. It will begin with insight. Another consequence of patience is preservation. A civilization that expects to exist for thousands of years must prioritize protecting its own continuity. That means preventing self-destruction, maintaining ecological balance, and managing technological risks. Advanced tools amplify both creation and destruction. Nuclear energy can power cities or end them. Artificial intelligence can expand knowledge or destabilize societies. Surviving long enough to attempt interstellar travel requires mastering restraint as much as innovation. This introduces a subtle shift in values. Speed becomes less important than reliability. Expansion becomes less important than stability. Novelty becomes less important than wisdom. This does not mean stagnation. It means choosing which forms of progress matter most. Then there is the role of time in shaping perspective. When a civilization stops rushing, it begins to notice patterns invisible at short scales. Climate cycles, social dynamics, technological feedback loops. Understanding these patterns allows better planning. A civilization that can think in centuries is less likely to sacrifice long-term survival for short-term gain. Alpha Centauri, in this context, becomes a horizon rather than a goal. It sets direction without demanding arrival. Another benefit of patience is that it allows ethical frameworks to mature. Rushing into interstellar travel risks repeating old mistakes, exploitation, domination, and disregard for unknown environments. Waiting allows humanity to debate, reflect, and refine its principles. Should untouched worlds be preserved? Should life, if found, be protected at all costs? Should expansion ever override caution? These questions cannot be answered quickly. They require cultural consensus, not technical fixes. Patience gives space for that consensus to form. There is also the possibility that patience reveals alternatives. Perhaps the most efficient way to reach Alpha Centauri is not through propulsion, but through understanding space-time more deeply, not through shortcuts, but through alignment with physical laws we do not yet fully comprehend. Quantum mechanics and general relativity remain incomplete when combined. Dark matter and dark energy shape the universe in ways still poorly understood. Future insights could reshape concepts of distance, energy, or interaction in ways currently unimaginable. This is not a promise, it is a possibility. But possibilities only matter to civilizations that survive long enough to encounter them. Then there is another effect of waiting that is often overlooked. Patience changes the meaning of success. If a civilization expects to endure, it does not need to achieve everything now. It can afford partial victories, incremental understanding, gradual refinement. This reduces desperation. Desperation leads to shortcuts. Shortcuts lead to catastrophe. A patient civilization can afford caution, and caution is essential in a universe that punishes mistakes harshly. Space does not forgive easily. Then there is the quiet psychological shift. A civilization that does not rush toward Alpha Centauri may begin to appreciate the depth of what it already has. Earth, with all its complexity and diversity, becomes not a stepping stone, but a masterpiece. Learning to live sustainably on one planet may turn out to be more challenging and more meaningful than spreading to many. This does not eliminate the desire to explore. It grounds it. Exploration becomes a choice, not an escape. Another important consequence of patience is memory. Civilizations that rush often forget. Civilizations that endure remember. They build archives, institutions, and traditions designed to preserve knowledge beyond individual lifetimes. They treat science as a long conversation rather than a race. In such a civilization, Alpha Centauri becomes part of a shared narrative, an ongoing question, rather than an urgent demand. Children grow up knowing that the universe is vast, that travel is difficult, and that understanding matters. This shapes expectations. It reduces frustration. It encourages humility. And perhaps this is the most important outcome of patience: humility. The universe is not obligated to be accessible. It does not exist for our convenience. Accepting this does not diminish human ambition. It refines it. It shifts ambition from conquest to comprehension, from speed to significance. So when we ask how long it would take us to go to Alpha Centauri, patience suggests a different answer. Not how fast can we get there, but how long can we last? Because only a civilization that lasts long enough will ever truly face the question of interstellar travel with options worth choosing. Alpha Centauri will wait. It has waited billions of years already. The question is whether humanity can learn to wait with it, and if it can, then perhaps the journey to the stars will not begin with urgency or desperation, but with calm, confidence, and understanding. And that brings us to the final reflection. If patience reshapes the future, what does that say about the ultimate fate of human exploration? that is where the story concludes. If patience reshapes the future of exploration, then one final layer of meaning begins to emerge. Not about technology, not about distance, but about purpose. Because once urgency fades, humanity is left with a quieter, more difficult question. Why explore at all? For most of history, exploration was driven by necessity: food, land, survival, advantage. Later, it was driven by competition, prestige, and power. In space, especially beyond the solar system, those motivations lose their force. Alpha Centauri does not offer immediate resources. It does not promise quick survival. It does not solve Earth's problems. So if humanity ever chooses to reach it, the reason will not be desperation. It will be meaning. This marks a profound shift in how exploration is understood. Exploration becomes less about what we gain and more about what we affirm. Affirming curiosity as a value. Affirming continuity across generations. Affirming that understanding the universe matters, even when it offers no immediate reward. In this sense, interstellar exploration becomes philosophical. It is a statement about what kind of intelligence humanity believes itself to be. A species that only acts when forced, or a species that chooses to understand, even when it is difficult. This distinction matters because civilizations that survive long enough to consider interstellar travel are not defined by their power, but by their restraint. They have learned, perhaps painfully, that not every capability must be exercised and not every frontier must be rushed. Alpha Centauri becomes a test not of engineering, but of wisdom. Then there is the idea of continuity beyond biology. Human bodies are temporary. Even with advanced medicine, individual lifespans are limited, but knowledge, culture, and purpose can persist far longer if they are protected. A civilization thinking about Alpha Centauri must confront its own mortality and ask what deserves to last. Is it territory? Is it identity? Is it understanding? These questions force clarity. Interstellar ambition strips away superficial goals. It reveals what a civilization truly values, because the cost is so high that only the deepest motivations survive. Another layer of purpose appears when we consider silence. So far, the universe has not spoken back. No confirmed signals. No undeniable signs of intelligence. This silence, often called the Great Silence, raises unsettling possibilities. Perhaps intelligent civilizations are rare. Perhaps they destroy themselves. Perhaps they choose not to expand. Perhaps they observe quietly. Whatever the reason, the silence itself carries meaning. It suggests that longevity may be more difficult than intelligence, that reaching the stars is not inevitable. If humanity ever sends something to Alpha Centauri, it may do so not as part of a cosmic crowd, but as a lone voice, and that changes the tone of exploration. It becomes less about competition and more about responsibility. Because if intelligence is rare, then preserving it matters. Preserving curiosity matters. Preserving understanding matters. Another dimension of purpose emerges when we think about memory across cosmic time. The universe will outlast humanity. Stars will continue to burn long after Earth is gone. Galaxies will drift apart. Eventually, even stars will fade. Against that scale, human existence is brief. But meaning does not require permanence. It requires coherence. A civilization that chooses to explore, carefully, patiently, responsibly, leaves a trace not in matter, but in pattern, a pattern of curiosity. a pattern of restraint, a pattern of awareness. Sending a probe to Alpha Centauri, even if it never arrives intact, would still be an act of meaning. It would say, we tried to understand more than our immediate surroundings. That matters. Then there is the internal effect of having such a goal. Even if humanity never reaches Alpha Centauri physically, aiming for it shapes behavior. It encourages long-term planning. It rewards cooperation over conflict. It elevates science, education, and preservation. Goals that lie far beyond immediate reach often produce the healthiest forms of progress because they cannot be rushed. They demand discipline. They expose weaknesses. They reward patience. Alpha Centauri functions as such a goal, not because it must be reached, but because it organizes ambition in a constructive way. Another subtle effect is humility toward the unknown. Interstellar distances remind humanity that the universe does not bend to desire, that knowledge has limits, that control is partial at best. This humility is rare in technologically advanced societies. Without it, power becomes dangerous. With it, power becomes careful, and care may be the defining trait of any civilization that endures long enough to look beyond its home star. Then there is the idea of stewardship. If humanity learns to think in cosmic timescales, it may begin to see itself not as an owner of Earth, but as a caretaker, responsible for preserving a rare configuration of life and intelligence. Interstellar thinking encourages this perspective. You do not abandon a fragile home lightly when you understand how rare such homes are. Alpha Centauri, ironically, may help humanity appreciate Earth more deeply than ever before. And finally, there is the personal dimension. For individuals alive today, Alpha Centauri will remain unreachable. No mission launched now will arrive within a human lifetime. No personal journey will be completed. But meaning does not require completion. It requires contribution. Planting trees whose shade you will never sit under. Building knowledge you will never fully use. Asking questions whose answers belong to the future. These acts define civilizations that last. So when we ask how long it would take us to go to Alpha Centauri, the most honest answer may be this: it would take as long as it takes humanity to become the kind of civilization for which the journey makes sense. Not technologically, but ethically, culturally, philosophically. Alpha Centauri is not calling humanity forward. It is holding up a mirror. And in that mirror, the question is no longer about stars. It is about us. And that leaves one final reflection, quiet but unavoidable. If humanity never reaches Alpha Centauri, what will matter most is not the distance left untraveled, but the wisdom gained along the way. And that is where the journey comes to its final pause. In the end, Alpha Centauri does not demand an answer. It does not ask us to arrive. It does not promise reward. It does not care whether we ever cross the space between us and it. And that may be its greatest lesson, because the question, how long would it take us to go to Alpha Centauri, begins as a technical curiosity, but it ends as something much deeper. It becomes a question about limits. Not only the limits of propulsion or energy, but the limits of intention, patience, and meaning. Alpha Centauri sits just far enough away to force honesty, close enough to be tempting, far enough to resist shortcuts. It strips away illusion. It reminds us that the universe is not arranged for convenience. Distances are real. Time is costly, energy has consequences, and not every desire can be satisfied simply because it exists. This confrontation with reality is uncomfortable, but necessary, because throughout history, humanity has often mistaken possibility for entitlement. We have assumed that if something can be imagined, it must eventually be achieved. Space challenges that assumption. It introduces a different ethic, one where imagination must negotiate with endurance. In that negotiation, something important happens. Ambition becomes reflective, curiosity becomes careful, progress becomes measured. This does not weaken humanity, it matures it. Alpha Centauri teaches that there is a difference between seeing and reaching. The universe allows us to see very far. Light carries information freely across vast distances. Knowledge flows easily compared to matter. This imbalance is not accidental. It suggests that the universe is structured to favor understanding over expansion. To know is easier than to possess. To observe is safer than to invade. This realization reshapes the role of intelligence itself. Perhaps intelligence is not meant to spread rapidly, consuming space. Perhaps it is meant to concentrate, deepen, and refine, to learn how reality works before attempting to rearrange it. If that is true, then Alpha Centauri is not a destination waiting to be conquered. It is a boundary waiting to be respected. This does not mean humanity should abandon the dream of interstellar travel. Dreams matter. They orient effort. They shape values. They define direction. But dreams must evolve. A childish dream demands immediacy. A mature dream accepts delay. The dream of Alpha Centauri may not belong to this century, or even this millennium. And that is not failure, it is scale. Human history is short compared to cosmic history. Modern civilization is shorter still. We are early in the story, not late. Expecting interstellar travel now is like expecting ancient civilizations to launch satellites. The knowledge base had not yet formed. The social structures had not stabilized. The understanding was incomplete. Time was missing. Time may still be missing. And time is not an enemy. Time is a resource. Given enough time, civilizations either learn restraint or they disappear. The universe does not rush them. It waits. Alpha Centauri has waited billions of years already. It will continue to wait. This patience reframes the idea of success. Success does not require arrival. It requires survival with meaning. A civilization that understands Alpha Centauri, its distance, its physics, its implications, and chooses not to rush blindly toward it, has not failed. It has demonstrated awareness. And awareness is rare. Then there is the quiet truth that often goes unspoken. Humanity does not need to go to Alpha Centauri to matter. Meaning is not proportional to distance traveled. It is proportional to understanding achieved. The same intelligence that wonders about distant stars is the intelligence that can protect fragile ecosystems, preserve knowledge, reduce suffering, and build continuity across generations. Those achievements are not smaller than interstellar travel. They are prerequisites for it. Without them, reaching another star would be hollow. With them, even staying home gains cosmic significance, because Earth, viewed honestly, is already extraordinary. A planet with liquid water, complex chemistry, stable climate cycles, and billions of years of evolutionary history. A place where matter became aware of itself. In a universe that appears mostly hostile to life, Earth is not ordinary. It is miraculous. Alpha Centauri does not diminish that miracle. It highlights it by showing us how rare such conditions may be, by showing us how difficult it would be to recreate them elsewhere. This realization does not trap humanity. It grounds it. It turns exploration into stewardship, and stewardship into purpose. Then there is the final layer of meaning, the one that emerges only when all others are stripped away. Alpha Centauri reminds us that not all questions are meant to be answered quickly. Some questions exist to shape how we think, not what we do. How long would it take us to go there? Should we go? What would it cost? What would it change? These questions are not instructions. They are mirrors. They reveal values, fears, and aspirations. They show us whether we are driven by impatience or by understanding, by escape or by responsibility, by conquest or by curiosity. And perhaps the most honest answer humanity can give right now is this: we are still learning how to be here, still learning how to live on one planet without destroying it, still learning how to wield power without losing wisdom, still learning how to think beyond ourselves. Alpha Centauri does not demand that we arrive before we learn these lessons. It waits. The stars are not calling us forward urgently. They are inviting us to grow quietly, to endure, to understand. And if one day, far in the future, humanity does send something across that distance, it will not be because we rushed. It will be because we lasted, because we learned to think in centuries, because we learned to value continuity over conquest, because we learned that exploration is not about how far you go, but about how deeply you understand your place in the universe. Until then, Alpha Centauri remains what it has always been: a nearby star, a distant mirror, and a reminder that the greatest journeys often begin not with engines, but with patience